Welcome back. If A is an m by n matrix with columns a1 through an, and if X is an Rn, then the product of A and X, matrix A, vector X, denoted by AX, is the linear combination of the columns of A and the corresponding entries in vector X as the weights. Okay, so what we're going to do is we're going to take this first matrix. That's going to be matrix A, and it's going to have vectors listed in it and columns, depending on the size is how long the columns are. Vector X, now it will need to match however many vectors are in A. That's going to be the number of entries in vector X. But anyway, like we calculated vectors and weights earlier, once you're multiplied A1 times X1 plus A2 times X2 and so forth till you get to the end AN times XN. Okay, so let's look at an example. We're going to take matrix A, which is a 2 by 3, and we're going to multiply it by vector X. If you take each entry in vector X times each column of A, then we have 4 times 1, 0, plus 3 times 2, negative 5, plus 7 times negative 1, 3. Second entry, second column, third entry, third column. 4 times 1, 0 is 4, 0. 3 times 2, negative 5 is 6, negative 15. And 7 times negative 1, 3 is negative 7 and 21. Now, 4 plus 6 plus negative 7, the top row totals out to 3. 0 plus negative 15 plus 21 is 6. So we've successfully multiplied A and X together. Another example. A is a 3 by 2. 3 rows, 2 columns, and we're going to multiply that by vector X, which has 2 entries. Top entry of X times, well, let me rephrase that. First entry of X times first column of A. So 4 times 2, 8, negative 5. Second entry of X times the second column of A. 7 times negative 3, 0, and 2. Multiplying using your scalar product, that's 8, 32, and negative 20. 7 times these three values is negative 21, 0, and 14. After the multiplication's done, then you add based on location, 8 plus negative 21, 32 plus 0, and negative 20 plus 14 to get your result. For vectors 1, 2, and 3 that are in Rm, write the linear combination 3v1 minus 5v2 plus 7v3 as a matrix times a vector. Okay, so we've got v1, v2, and v3 multiplied by 3, negative 5, and 7. So if we write this down and we separate first entry, first column, vector 1 is multiplied by 3, vector 2 is multiplied by negative 5, and vector 3 is multiplied by 7, and that sets it up as AX. Basically, you're just going the opposite direction of the previous slide. Okay, so let's recall these two equations, 3 unknowns, 3 vectors actually. Let's think of it that way as vectors. X1, there's a coefficient of 1, but there's not 1 here, so that's a 0. X1 times 1 and 0 x2 has 2 and negative 5, x2 has 2 and negative 5, x3 has a negative 1 and a 3, and that's set equal to vector 4, 1. This system is equivalent to this setup, which is also equivalent to these three vectors in matrix A times vector X, which has 3 entries, x1, 2, and 3, and it's still equal to 4, 1. The last form is called a matrix equation. Matrix A times vector X equals vector B. The equation AX equals B has a solution if and only if B is a linear combination of the columns of A. Now, in the previous video, we put these together, solved, and got our weights. These are basically the weights. So what we're going to do is we're going to find out if AX equals B is consistent. That means whether it has one unique solution or infinitely many, and whether or not B is in the span of all the vectors from matrix A. Let A be an m by n matrix. The following statements are logically equivalent. For each vector B in Rm, the equation AX equals B has a solution. For each B in Rm, each B in Rm is a linear combination of the columns of A. The columns of A span Rm, and what you'll find is if all that's true, A will have a pivot position in every row. Every row. So let's check out this example. Matrix A times vector X, x1 times the first column, x2 times the second column, and x3 times the third column. Multiplying, that's 2x1, 3x2, 4x cubed, to the subs 3. I'm having trouble talking tonight. So anyway, multiply across the tops, then multiply across the bottoms. Negative 1x1, 5x2, negative 3x3. Okay, so can we be more efficient? Basically, it's just another way to multiply. I will do a multiplication video for the TI-84, and I'll post it after this one. You can do it, instead of breaking it up one entry and one column at a time, you can actually think of take your vector X, lay it flat, and do a series of multiplying and adding. 4 times 1 plus 3 times 2 plus 7 times negative 1. That will be your top row. Then take this, think of it as lay it flat against row 2. 4 times 0, 4 times negative 5, 4 times 0, 3 times negative 5, and 7 times 3. You just have to think of this as laying it over and then lining them up. 4 times 0, 3 times negative 5, 7 times 3. The grand total, 4, 6, that's 10, minus 7 is 3. 0 minus 15 plus 21 is 6. So that gives you an answer for multiplying. If you find a matrix of all zeros except for the main diagonal, and that main diagonal is all ones, that's called an identity matrix. And it's basically like in our numerical system, if you take 1 times any non-negative number, the answer is that non-negative number. Like 1 times 5, still 5. 1 times negative 10, that's still negative 10. Same thing here, an identity matrix times any vector of an appropriate size will be the same. And this is just kind of the in-between steps to show that. Identity matrix times a vector will be that vector. And I think I'm going to cut the video off here, and then I'll pick up here with a second video.